All right, today we're pulling back the steel doors on one of the most critical, but honestly often overlooked pieces of hardware in the entire industrial world, the motor control center. Just picture any modern factory. You've got robots, conveyors, pumps. It's this incredible symphony of motion. And all of it, every last bit, is powered by electric motors. But have you ever stopped to think, with hundreds of motors running all at once, what keeps the whole thing from just turning into total electrical chaos? What's the unseen nerve center that's conducting it all? Okay, let's get into it. Well, the answer to that question is something called a motor control center, or MCC for short. And believe me, it is the unsung hero of industrial automation. To really get why an MCC is such a big deal, you first have to understand the problem it's built to solve. Imagine a massive facility, motors spread out all over the place. How do you control them all? How do you protect them? And, the big one, how do you keep your people and your expensive equipment safe? See, the challenge is that every single motor needs its own little package of gear, a way to turn it on and off, and a way to protect it from electrical faults. Now, if you just scattered all those individual controls around the plant floor, well, you'd have a tangled, inefficient, and frankly, a really dangerous mess. And this is exactly why the industry needed a standardized, centralized solution. And that solution is the MMC. The National Electrical Manufacturers Association, NEMA, gives us this very precise definition. Now, I know it sounds a little technical, but it really nails it. It's basically a big, floor-mounted cabinet that centralizes all the power and control for a whole bunch of motors in one safe place. Okay, so we know what an MCC is for. Now, let's get to the really interesting part. Let's crack one open and see what's actually going on inside one of these steel cabinets. Think of it like we're taking a journey from the outside in. We're opening the door on this system to see exactly how it's built to manage just immense electrical power, not just safely, but logically. So this right here is the basic skeleton of the MCC. You've got these main steel frames. Those are called the vertical sections. Running across the top, that's the horizontal power bus. Think of it as the main artery for all the electricity. Then, dropping down into each section, you've got the vertical bus bars, which tap into that main power line. And on the sides, you have wireways to keep all the cabling neat and tidy. It's all about creating order from chaos. Here is the absolute best way to think about it. That horizontal bus is the main interstate highway for electricity, just carrying all that raw power. The vertical bus bars? Those are the exit ramps, delivering that power exactly where it needs to go inside each section of the cabinet. Simple as that. Now that we've seen the main structure, let's zoom in even further. We're going from the skeleton down to the individual modules that are the real brains of the operation for each and every motor. And this is the real beauty of the MCC's design. It's totally modular. Every motor out there on the plant floor is controlled by its own personal little drawer or unit that just plugs right into the main structure. This one unit has everything needed to safely run that one motor. And each of these units has three absolutely critical jobs. First, you've got a disconnect handle on the outside. That's for a person to manually and safely kill the power for maintenance. Second, it has overcurrent protection. That's a fuse or a circuit breaker, and its job is to guard against a massive instant surge from a short circuit. And third, you have the motor starter. That includes a contactor for normal on and off switching and an overload relay for a whole different kind of protection. So that brings up a really important question, right? A short circuit is, a huge catastrophic event. But what about a slower, more subtle problem? What happens when a motor is just trying to do too much work? Like, say, a conveyor belt jams up and the motor is straining and straining to keep it moving. That is precisely the job of the overload relay. And the best way to think about it is like a smart thermostat for your motor. It doesn't care about a massive instant electrical surge. Instead, it's watching the motor's current draw over time. If that motor works too hard for too long, it starts to get hot. And the overload relay senses this and shuts it down safely before any permanent damage is done. This difference between a slow burn overload and a sudden, violent short circuit is so critical for safety that it really deserves its own section. So let's break down how the MCC protects against both kinds of electrical mayhem. So just to put it all together, the overload relay handles the working too hard problem. The fuse, or the circuit breaker, handles the catastrophic short circuit problem. You need both for complete protection. Which, of course, brings us to one of the classic debates in this field: fuses or circuit breakers? This table really lays out the key differences. Check out the interrupting rating. That's the maximum amount of fault current a device can safely stop without exploding. Fuses are incredible. They can handle huge currents, up to 300,000 amps, and they react ridiculously fast. But here's the catch. They're a one-and-done device. Once it blows, you gotta replace it. A circuit breaker can't handle quite as much current, and it's a bit slower, but, and this is a big but, you can just reset it. So what does that really mean on the factory floor? Well, when a fuse blows, the average downtime to safely shut everything down, find the right replacement part, and get it installed is about 45 minutes. And to reset a tripped circuit breaker? 5 minutes. Just 5. That 40-minute difference, multiplied by dozens of motors across an entire facility, well, that can mean thousands, even hundreds of thousands of dollars in lost production. So yeah, choosing between a fuse and a breaker, it's not just a technical detail, it's a huge operational decision. And all this brings us to the modern MCC. It's not just a simple on-off switch anymore. It's a piece of technology that's been shaped by decades of rigorous safety standards and really incredible advancements. Look, these devices are not built in a vacuum. They have to follow super strict standards to even be considered safe. Here in North America, that's mostly NEMA. In much of the rest of the world, it's IEC standards. And compliance isn't optional. It's absolutely critical for safety and for making sure all this different gear can actually work together. And we're talking about an incredible level of detail here. Documents like NFPA 79, that's from the National Fire Protection Association, and UL 508A for control panels, these are the literal rulebooks. They dictate everything from how far apart wires have to be to how components are tested, all in the name of building systems that are safe and reliable. But modern MCCs are about so much more than just safety. They're about being smart. Instead of just slamming a motor on at full speed, we now have amazing devices like soft starters, which gently ramp up the voltage to reduce that jarring mechanical shock. And even more advanced are variable frequency drives, or VFDs. These things can change not just the voltage, but the frequency of the power, giving you precise, continuous control over a motor's speed. This is an absolute game changer for things like fans and pumps, where fine-tuning the speed can save an enormous amount of energy. So we've gone from a simple switch to a centralized cabinet, and now to an intelligent, networked system. And it really leaves us with a fascinating final thought. As all these components get smarter and smaller and more connected, what happens when every single motor in a factory basically has its own brain? What does the future of industrial motion even look like then?